In this video, we explain the variation of the reaction Gibbs energy with concentration explicitly. Okay, so we come to the crux of this chapter, and the equation that we're going to derive from this video is what I consider to be the most important equation in all of thermodynamics. Here's the idea. We have a reaction A to give B, which might be reversible, and what we want to do is calculate the value of the reaction Gibbs energy under any conditions. Okay, so not only at the standard state, but under any possible concentrations or partial pressures of the reagents and product species. Now, have you seen that the reaction Gibbs energy is defined simply as the balance of the chemical potential between reagents and products. Okay, so that is the chemical potential of products minus the chemical potential of reagents. Now, we can even enhance this to make it a little more general and assume that the stoichiometric coefficients are not 1, but they are numbers which are denoted by the lowercase letters a and b. If that's the case, then what this expression turns into is simply the chemical potentials multiplied by their stoichiometric coefficients, much as we have seen for other thermodynamic properties. Alright, so what we do now is use our knowledge of chemical potentials to substitute those values into these values right there. Okay, so our chemical potential, we said that the place-holding expression that we're going to be using is this. Chemical potential is equal to the chemical potential at a reference plus RT natural log of the activity. Okay, so we come to this expression and we find that this is going to be equal to delta Rg is B multiplied by the chemical potential of B at the reference plus RT natural log of the activity of B, and then minus A multiplied by the chemical potential of A at the reference plus RT natural log of the activity of A. Okay. Now, what about the reference? Well, the reference in most of our problems, actually in all of our problems, is going to be the standard state. Okay, and then what it means is that we can replace this reference by the standard state, which we denote as this symbol. Okay, and that is also going to inform what are the activities going to look like, as you will see in a little bit. Again, a reminder of what the standard state is. For gases, the standard state is going to be 1 bar of pressure, and then for solids in a solution, it's going to be 1 molar concentration. If you have a solid, then it turns out that the activity will be 1. If you have a liquid, the activity will also be 1, as long as the liquid is the only liquid present in the solution. Okay. Great. With that, what we can actually do is then operate through this expression and see if we can consolidate it somehow. Delta Rg is going to be equal to B times the chemical potential of B at the standard state plus B, RT natural log of the activity of B minus A mu of A at the standard state minus A RT natural log of the activity of A. Okay, in the next step what we're going to do is just group together these two terms, and then in this expression we're going to realize that you have here the stoichiometric coefficients multiplying the natural log, and it turns out that they can actually get into the natural log as powers. Okay, so let's do that. Delta RT is going to be equal to B mu of B at the standard state minus A mu of A at the standard state plus RT natural log of the activity of B to the power of B minus RT natural log of the activity of A to the power of A. Okay? Alright, now examine this expression a little bit more closely. Alright, let's see what we have right here. Notice that this is the chemical potential of products minus the chemical potential of reagents at the standard state multiplied by the appropriate stoichiometric coefficients. Right? When we come to this definition, look that this is very similar to that. So actually what we're calculating here is just the reaction Gibbs energy at the standard state, because these are the chemical potentials at the standard state. Okay, so then our expression is going to be delta Rg is equal to delta Rg plus at the standard state plus this correction. Alright, what is that we can do here? Well, here we can take on factor of the Rt, and then this expression turns into Rt, and then you will have the natural log of a sub b to the b minus the natural log of a sub a to the a. But the difference of two natural logs is the natural log of the ratio. So this turns into the natural log of the activity of b to the power of b over the activity of a to the power of a. Okay? Right. Here we actually have carried out this derivation, assuming that there's only one reagent and one product species, but we can make it more universal, okay, by assuming that there's two reagents and two product species, right? So we can turn the reaction like this, okay, to generate C plus D to the D, and there's actually not going to be any changes, right? The only change here is that here we will have that we started the derivation with the chemical potential of products, which will be C mu C plus D mu D minus the chemical potential of reagents, A mu A minus plus B mu B. Okay, you carry out this out, and the expression is going to be the same. The only difference is that you're going to find here that when you come to this final term, these are simply going to be the activities of products, A sub C to the C, and A sub D to the D, and then divided over the activities of reagents to the powers of the appropriate stoichiometric coefficients. A sub A to the A, and the activity of B to the power of the stoichiometric coefficient of B. Okay. Now, this is what we called the reaction quotient, Q. Okay, the reaction quotient. And again, it's just the activities of products over the activities of reagents, and each of those activities should be modified by the elevated to the power of the stoichiometric coefficients. If all of those stoichiometric coefficients are 1, then the reaction quotient will simply be the activities of products divided over the activities of reagents. Okay, so this is actually going to be the final expression, and I consider this to be the most important reaction in all of thermodynamics. Okay? Why is this reaction so important? This reaction is very important because it allows you to predict whether a reaction is going to be spontaneous or not under any set of conditions. Right? Notice that in the homework problems we will actually see what these activities are all about, but there are going to be either partial pressures or molar concentrations or any measure of concentration that we can think of. Right? So here is where we're actually going to be inputting, we're going to be plugging in the actual concentrations under which you're interested. Okay, so for example, if this is the reaction, the metabolism of glucose with oxygen to generate CO2 and water, okay, those will actually be the concentration of glucose in your cells, the partial pressure of O2 inside your cells, and then the concentration of CO2 and water that you actually get in. So that means that you're not only calculating the reaction Gibbs energy at the standard state, which is what we know how to calculate, that number we already know how to calculate, but actually we can see that we can take that further and extend it to the prediction of spontaneity and how much work you can potentially extract out of this process under any conditions that we want, right? So there's a lot of power in this expression, and notice that it's actually very beautiful. It's very simple. Right? The Gibbs energy is equal to the Gibbs energy at reference, which in our case is going to be the standard state, plus a correction from the fact that these activities, those concentrations might not be the concentration of the reference. Okay, so when you think about this expression like this, there's beautiful symmetry with what we were writing about the chemical potentials, where the chemical potentials were the chemical potential at a reference plus a correction from the fact that you might not be at the reference. Okay, so notice how these expressions that we worked out in the prior chapter have carried over now to these molar Gibbs energies, which again is a property of a full reaction. Right, so a couple of examples about the reaction quotient, and then we'll finish this video. Right, so for example, how do you write the reaction quotient for the reaction N2 gas plus O2 gas to generate 2 molecules of NO gas. Well, that reaction quotient is going to be equal to the activity of products, so that's going to be the activity of NO to the stoichiometric coefficient, to the power of the stoichiometric coefficient, over the activities of reagents, A, N2, A, O2. Okay, but these are gases, so the way that we replace activity by pressures is going to be as follows. Okay, that is going to be the pressure of NO that we have over the pressure of NO at the standard state to the power of 2, and then we'll have here the pressure of N2 over the pressure of N2 at the standard state times the pressure of O2 over the pressure of O2 at the standard state. Okay? We also know what the pressures of the standard state are, and those are going to be 1 bar. Okay, so this expression is going to be turned into the pressure of NO over 1 bar, and all of this is to the power of 2, and this is the pressure of N2 over 1 bar times the pressure of O2 over 1 bar. Okay, so this is the example of how you write the reaction quotient for a particular reaction. And again, you can do the same thing for reactions in which you have solids in solution, and then the activities will be the molar concentrations over the concentration of the standard state, which will be 1 molar. And again, if you have a solid, the activities is going to be equal to 1. And if you have a liquid, and that's the only liquid in the reaction, the activity will also be 1. So from that discussion, you can actually write the reaction quotients for any reaction that we know, and then you can go on and calculate whether the reaction will be spontaneous or not, and how much work you can extract, how much non-expansion work you can extract from it using this expression.